All right, question number 17. We want the work done by the torque. And, if you really wanted to, you could probably do some crazy, work integral, taking, force and dx and, doing some kind of crazy integral like that. But I'd rather keep it simple. I know that work is change in kinetic energy. So let's look at the change in the kinetic energy of this wheel. So 1/2 I omega squared. 0 minus this is going to be the torque, is going to be the work done, since we're changing the kinetic energy to 0 from whatever speed it was at. So that's 1/2 times 0.04 times omega squared. So we get 10 revolutions in a second, huh? So that means the period is going to be, 1/10 of a second. So with that in mind, let's see what we can do here. So I know that the speed is 2 pi r over t for something spinning round and round. And if we divide that by r, we realize that omega is simply 2 pi over t. So we get negative 1/2 times 0.04 times 2 pi over a period, times a frequency of 10. And so when we kind of keep all this together, let's see, what am I missing? So, what if and I'm going to square this. So here we go. We're going to end up getting here negative 1/2 times 0.04 times 400 pi squared. And let's do some cancellation. So this ends up being 4 times 4, which is 16, divided by 2 is 8, so I'm getting negative 8 pi squared, which is choice E. All right. Now for 18, we got to balance torques, and we have to balance forces. So first, let's balance the forces. So this hinge applies a force in the y direction, which I'll call hy, and a force in the x direction that I'll call hx. So let's actually balance forces first. So I got hy plus t sine theta minus w equals 0. That's not going to help. Now let's look at the torques. We'll measure the torque with respect to this point here. So hy at 0 minus w at L over 2 plus t sine theta at L balances out. So we balance the torques as well. This ends up being 0, so we end up getting WL over 2 equals t sine theta times L. The L's cancel. And so what I'm finding is that choice B is the answer, because T equals W over 2 sine theta. Nice. All right, we want to know the speed of the center of the mass if we hit this thing on the edge. We're talking about center mass speed, so we don't need to worry about any kind of weird angular stuff. We'll just do conservation of momentum. So mv naught equals m plus m v final. These cancel, and so we're getting here, this is momentum conservation. That's choice C. All right, here, notice we got 3 and 2 and then 2 and 3. That means not only is momentum conserved, but kinetic energy is conserved. People screwed this up on the free response too. This got messed up on free response. Okay, you have to conserve momentum. That's fine, but a collision is elastic, perfectly elastic in AP physics definition, only if both momentum and kinetic energy is conserved. Well, momentum's always going to be conserved, so you've got to make sure you conserve kinetic energy as well. So that is the next page of the exam.